Hi, my name is Simon, and I'm presenting to you Steering Self-Supervised Learning Beyond Local Pixel Statistics. This is a joint work with Hailin Jin and Paolo Favaro. Our goal is to learn image representations without human supervision. We believe good image representations should capture both local and global image statistics. Local statistics capture the distribution of nearby pixels, for example texture, and global statistics the distribution of faraway pixels, such as shape. A recent work has shown that supervised features are often biased towards local statistics and that forcing networks to focus on global statistics improves their generalization. So how can we push self-supervised learning towards learning global image statistics? Our approach is to design tasks where relying on local image statistics is not sufficient. For example, can you tell from these local image patches if and how the image has been transformed? Learning only local image statistics is generally not sufficient for this task. Only when observing the global statistics are we able to recognize if images have been warped, inpainted, rotated, or not transformed at all. We identify such a recognition of image transformations that preserve local statistics but alter global statistics as a framework for self-supervised feature learning. We observed that several existing methods fit this framework. For example, in puzzle solving the local patches are not altered and only the global arrangement of the patches is transformed. This provides a new perspective on why such methods learn good features. Following this framework, we build new self-supervised learning tasks by training a classifier to recognize the following set of image transformations. Random image warping. We introduce a new transformation based on local inpainting called LCI, image rotations as proposed in prior work, and the case of no transformation. This framework is simple and can easily be extended by changing the set of transformations. Our experiments show that considering a larger number of transformations generally yields better features. Let us now have a closer look at limited context inpainting. One approach to design a transformation following our principle is to modify images only locally. We therefore propose to transform images by learning to replace image patches such that local image statistics are preserved and global statistics are almost surely altered. To do so, we learn a generative model of image patches conditioned on a limited border of context pixels. Concretely, first we sample an image patch. We then erase all but a thin border of context pixels. We feed the erased patch through a patch inpainter network. The patch inpainter is trained via adversarial training against the patch discriminator. The inpainted patch is finally pasted back in the image. We call this transformation limited context inpainting, or short LCI. If the inpainter learns the natural distribution of image patches, replacing patches with LCI will result in images with natural local statistics and unnatural global statistics. To verify our approach, we pre-train an AlexNet to recognize a varying number of image transformations on STL10. Features are evaluated by training linear classifiers on frozen convolutional layers. We compare all combinations of 2, 3, and 4 transformations. We observe a consistent improvement of feature performance with an increasing number of transformations. Note that the performance of transformations depends heavily on the data domain. If a transformation can be recognized solely based on local statistics, feature performance suffers. To illustrate this, we used our method on the CelebA dataset and evaluate features on face attribute recognition. We noticed that rotation prediction can be solved by only observing local image patches, like the orientation of the eyes. Global statistics do not have to be learned, and the features perform worse compared to other transformations. LCI generalizes better to this data. We perform established feature learning benchmarks by pre-training on ImageNet and transferring the learned features to new tasks and datasets. Here, we evaluate the features with linear probes on the places dataset and compare to prior self-supervised methods. Our features achieve state-of-the-art performance, and our best result is even on par with supervised pre-training on ImageNet. More results and comparisons can be found in the paper. Thank you for your attention. Please visit our poster and project page for further details.